Thanks very much. Good morning, everybody. It's a pleasure to see you all here at SC. I hope you had an interesting first few days. What I'm going to talk to you about is visualization on GPU Accelerated Supercomputers. And actually, the real content of my talk is going to be slightly shifted from this title, but we had to submit the title for production of the programs before we made the announcement about the HPC visualization containers, and so I couldn't actually put the container word in there. Anyway, so as you all know, visualization is instrumental to the scientific to computational science workflow. While it sometimes seems that you're just producing some pretty pictures, there is actually inherent information that you try to extract from the data by looking at it via pictures. So in this particular case here, we have some volume visualization of a tornado in Oklahoma, a simulation of a tornado. You would have the funnel clouds down here in the middle. That is what you typically see, or what you associate with the tornado. But this all up here is the large-scale structure that formed that tornado. And as you can see, there's so much intricate detail in the turbulent flow, for instance, that is really hard to analyze by either just staring at numbers or by making some cuts and looking at 2D renderings. So being able to interactively work with large, complex 3D objects is instrumental to the scientists to get a better understanding of the underlying physics. Now, obviously, visualization has been around for almost as long as we had computers, but it seemed like the interest in visualization has vanished a little bit after somewhere in the early 2000s. The large visualization packages have been open sourced, and then people were happy with just having access to ParaView, Visit, VMD, and there wasn't really a lot of demand for something more advanced on the rendering side. Interesting enough, over the past few years, there has been renewed interest in bringing advanced rendering techniques to the scientific visualization communities. And on top of that, there has been also different workloads that are starting to pop up on the HPC centers. So people are no longer just doing PDEs on supercomputers. They're not just solving partial differential equations, but people are doing data analytics, machine learning is coming in, artificial intelligence approaches. So that gives some new use cases for the visualization tools that were typically not designed for this type of workloads. On top of that, together with the advanced rendering algorithms that I mentioned, there's also new novel display devices, like virtual reality is starting to appear, and so, or people want to do some even augmented reality with the simulation data that is being produced. And so there's just a lot of new interest in the rendering and visualization space. Now, unfortunately, with this added use cases, there's also added complexity to the entire software stack that runs on the HPC systems. So here is just for traditional applications that run on GPU Accelerated Supercomputers, and you can see that for those hundreds of applications, there's thousands of different software stacks, libraries that need to be brought together, and it can make life really, really challenging for people who want to maintain these software packages. So there has to be an easier way of dealing with that. And maybe by now, and if you have been here in the theater before during the first few days of supercomputing, you probably have heard about our interest in containers. And so the idea is really to use containers to dramatically simplify the deployment of HPC applications. On the left-hand side, you see what typically happens today, right? You have a bunch of open source packages. In this particular case, it's packages from the deep learning space, but pick your favorite scientific simulation code, and it probably looks similar. So you have your open source frameworks, then you have underneath, you have the variety of different libraries, then you have to worry about having the right driver, depending on how things were compiled. There might be very tight connection to the driver or dependencies, and you have your host OS, and then finally you get down to the GPU. If you're lucky enough and you have really smart system administrators at your HPC center, then this is all taken care of you by them. But we don't want to put sysadmins out of their job, but it is also getting harder on them to maintain all these different packages. And as a result, oftentimes these codes are not optimized to utilize the GPUs that are in the systems. And so the simplicity with the containers is that you have your system hardware, you still have your host OS underneath, and then you have the Docker engine, which then runs these containers on top of your host OS. The entire application is bundled together with the libraries, the dependencies, the parts of the OS that you need, all together in a beautiful package that is maintained by somebody else. And so it's really much more of a pack and go kind of experience for the end user than having to bundle this stuff yourself. And so the way that we are dealing with that is that we announced the NVIDIA GPU Cloud for HPC, which is pretty much, at this time, it's a registry. So it's basically a service that you can create an account on that contains a collection of containers that you can pull down to your system and run on your particular HPC system. This registry contains general purpose simulation codes, predominantly at the moment out of the molecular dynamics space, but it also contains a bunch of visualization packages. And we have down here is the link to the NVIDIA GPU Cloud. So go there, create an account, and download your first containers. As I mentioned, at the moment we have a big focus on the molecular dynamics codes. In the future, we're moving to other types of applications. That's now on the solver side. For the visualization side, we follow exactly the same pattern. So what we've done is we built, at the moment, it's 3 container families that encapsulate open source tools, plus in all 3 cases, some modifications from us to give added value from GPUs. I'll go a bit into more details as we go on, but on one hand, we have packaged the pair view with the index scalable volume rendering solution. We have packaged ParaView with our optics ray tracing engine for having ray traced images in your ParaView visualizations. And the most exciting from my perspective, or the most interesting one on a technical level, is the coupling of ParaView with our Holodeck technology that gives you access to very high performance rasterized renderings utilizing latest generation OpenGL standards. In the same vein as the other containers, you can access them through the URL here, so nvidia.com/GPU Cloud. And one word of caution there, our other containers are built on a wrapper to the Docker engine called NVIDIA Docker. But unfortunately that NVIDIA Docker, well, Docker originally doesn't contain all the rendering libraries or pulls in all these rendering libraries. And so if you want to use our visualization containers, you have to install NVIDIA Docker 2. Now that's kind of the next generation Docker infrastructures anyway, so it might be now the time to make the migration to NVIDIA Docker 2. So how does that look like? After you've signed up to your, after you created your NGC account, you're ending up in this dashboard. And so you will see different repositories. On the left-hand side, you see these are now the deep learning repositories. Or on top of it, we also have the HPC visualization repos. And now in this case, I've selected ParaView with optics. And so you get the command how to pull this container. And you will also get the a brief README that describes how you would get this container off the ground on your installation. And as you can see, it also contains the link to NVIDIA Docker 2, in case you haven't installed that yet. Now, one thing you might wonder, and one thing that actually separates the visualization container story from the general purpose application story, is that for a general purpose HPC application, let's say a molecular dynamic simulation code, there you expect that everything runs on the HPC system, right? You might run across, I don't know, a handful of nodes, but you fire off the job and it runs there. For visualization, it's different. You eventually want to see pictures and you want to have interaction. For those of you who know ParaView, you know that you have a server-side component of ParaView and a client-side component. So if you want to set up your ParaView on top of containers, you actually need two containers, right? You need the container that sits on the server side, and you need the container that runs on the host side. And the way that we've bundled those containers, you don't need to worry about which one is which. You basically just have a slightly different run command, and I'm coming to that in a second. But you just pull down these containers onto the server and on the client, and then go through the motions of firing up those containers, and you're good to go. Now, one thing to remember there, and now that gets a little bit technical, but if you want to do any kind of OpenGL renderings, so if you want to have a GUI, for instance, or if you want to have advanced rasterization rendering, you're going to need some mechanism of dealing with your OpenGL context. That's just a data structure that somebody needs to maintain. Historically, in the Linux or Unix environment, that was typically the X server that was in charge of this context. And it is still today on many of the Linux desktops, the X server is responsible for managing the OpenGL context. Now, we've worked a lot, and I've also talked in this setting in the past about using EGL, which delegates this responsibility to the driver. That's typically useful in the server configuration where you don't want to fire up an X server just for maintaining an OpenGL context. And so we offer, given that we have those two use cases, we offer two flavors of our containers. On one hand, a container that's built against EGL, mainly geared towards the server configurations. And then we have a container built against GLX, so that takes advantage of the X server. That allows us to basically allows us to run the container on your desktop and interact with your X server, so you can pop up a window and you have the same GUI experience on your laptop or on your workstations as if you had installed ParaView on your system. All right, that was already a bit complicated, lots of hand waving. I hope you're still with me. Here in the next two slides, I'm just going to show you how this looks like mechanically. So for Docker, to pull a container, you need to log into the registry. I assume you've done this login step. But what we're doing here is just the two steps that are necessary to get the server-side container up and running. So the first command is really just pulling this container from our registry to your system. And that's just a Docker pull command. That's typical Docker lingo. And then the name of the container. And as you can see in my particular case there, I'm using the ParaView optics container. And after the colon, this is the so-called tag for this particular container. This is the EGL version, and we currently date them. As you can imagine, this is now brand new. There's still lots of rapid development. So right now, this is our the latest version of the container, which is yesterday or so, and we're still in the beta phase. So yeah, things might move a little bit over the next few days. But so this way you get the container, and then you have to run your container. In this particular case, it's the docker run command. That's your standard way of running a container. With selecting the runtime NVIDIA, we basically tell the container management system that we want to use all the goodies that are provided otherwise by NVIDIA Docker. And then there's a bunch of other commands, but basically what you're then telling is you want to fire up the container, and then at the end you have the command that it's being executed within the container, and that's in our case the PV server. Okay, so if you've ever run ParaView, this is it's not too shocking. There are a few things that are Docker specific, but at the end of the day, all you're doing is really fire up a PV server. Now, as you can imagine, the container gives you also some kind of encapsulation from the host operating system. But you probably want to have access to local files, or you want to maybe you have some fancy plugin that you want to communicate with the outside world. So those are all parameters that you have to specify on the command line, like which file systems will be mapped, which file systems on your host OS will be mapped into the container, so you can access the data from there. Okay, the second one, now this is a bit ugly, and we're still trying to figure out what the best way is to deal with that, but this is for the client side, and we want to do GLX. So we actually want to interact between our container on the client side with the X server on the client side. First part is again Docker pull command, and I just realized that I have a typo there on the slide. It should be the GLX container and not the EGL container there. I have it right down there, then again, there it's the correct form. So I'm pulling the container, and then finally I want to run the container. There's a bunch of files that I need to map into the container, and so you do that with the -v command. But finally, at the end of the day, all I'm doing is firing up ParaView. Now there's this bit in between, and that one is basically necessary to tell your local X server that it's okay that there's another application from working from somewhere, even running as a separate user, that this application should be allowed to connect to your X server. Completely agree, this is not beautiful right now. This is kind of bare metal. If you have great ideas on how to solve that in a very transparent way, we're more than happy to hear that. And I'm sure that this will change in the near future as well. One thing I wanted to point out here is, right, what I've specified on the command line as well is the URL for the ParaView server. Now, obviously, it wouldn't be your server.address, but it's you would specify the server address that you're connecting to. And you remember in the past slide we fired up the ParaView server on the HPC side. This one is on your client side. After that, you have a connection between the PV client running on your workstation with the PV server on the back end. Now, this is bad. I'm running out of battery here. So a few things just to the content of the containers. As I mentioned, we have on one hand one that offers an optics backend. Optics is our ray tracing engine that is now part of VTK. So if you go to the open source VTK Git repository, you will find a branch for optics. What we've done, we went one step further and integrated it also into ParaView. So in the same way as you can use other ray tracers within ParaView today, you can also use a GPU Accelerated optics-based backend. And then, as I mentioned, we have the index plugin, so our access to our volume renderer, and you can see a demo of that one running right over there on the outside. And finally, I just want to briefly touch on the Holodeck container. As I mentioned, Holodeck is our technology to give you access to highly efficient and optimized rendering engines. They're actually coming out of the consumer, of the entertainment space, i.e. from the gaming world. And so with this, you get access from within ParaView to this rendering engine, to this game engine in a seamless way. We had it up and running yesterday on that slide monitor. I hope we can fire it up again during lunch. But the idea here is really that you get access to all these beautiful shaders that people have developed over time to create these very beautiful renderings in a workflow that is familiar to the typical scientist. It also helps to make a better separation of concerns so that you can use an artist, if you have access to an artist, to help you soup up the scene or the renderings in a way that they become really high production value. That's a framework that artists are typically familiar with, whereas if you ask them to do beautiful renderings in ParaView, they typically are not so familiar with that toolchain. All right, and now I really have to apologize because I'm running out of battery very, very rapidly. Just wanted to say again, we have the access to the containers is via the NVIDIA GPU Cloud. You can find the documentation online. Have a look there to see what is possible, how you can use those containers. And with that, I'm at the end. Thank you very much for joining.